Hello all, myself Akash and Rishhanth. We are presenting our project on optimal code for the shift channel. So the objective of this presentation is we want to modularize the zero error codes for the shift channel, and we would exploit this modularity to construct optimal codes for the shift channel. So any input sequence to the shift channel x1 to xn can be considered as an n cell register, and each element xi can take values between 0 and p. A value of 0 means that the ith cell is empty, and non-zero value means that it contains a particle of type p. So the shift channel is characterized by two positive integers k1 and k2. So k1 here represents the minimum shift and non-zero particle undergoes, and k2 represents the maximum shift it undergoes. And one of the properties of the shift channel is that two non-zero particles cannot swap the cells or end up in the same cell. So essentially, the input sequence and output sequence that's obtained by deleting all the zeros are identical, and the amount of shift and particle undergoes is constrained by k1 and k2. So the notations for denoting such a shift channel is provided in the slides. Now, since the codes for a shift channel only depends on the difference between k2 and k1, it doesn't depend on the absolute value of k1 and k2. We consider the channel with 0, k instead of the general case of k1, k2, and we restrict ourselves to this for the further analysis. And so now we define what's called as an Hamming weight of a string, which is defined as the number of non-zero elements present in the string. And by definition, since the shift channel cannot add or delete any non-zero elements, the Hamming weight of the transmitted code and the input code is the same. So now two code words which have different Hamming weights can never have the same output sequence in the shift channel. So this is because in the shift channel, as we previously told, the Hamming weights are preserved, and so different Hamming weights in the input correspond to different Hamming weights in the outputs, and then their sequences will be different. So as a consequence of this, we can restrict ourselves to focusing on constructing optimal codes for sequences with Hamming weight W, fixed Hamming weight W, and then we can construct the overall zero error optimal code words by taking all such W's from 0 to n. Now, two code words x and y that have the same output sequences can have the same output sequences if and only if they have the same sequences of non-zero elements. Again, this is the property of the binary of the shift channel. And so now we define the indicator of a sequence as indicating if the sequence has the elements in the sequence have a zero or a non-zero elements as specified in the example. So so when x and y are inputs to a shift channel p, k, I of x and I of y are inputs to the shift channel 1, k, indicating its binary alphabets 0 and 1. So now two code words x and y over the shift channel having the same non-zero sequence can be confused while decoding if and only if their indicator counterparts I of x and I of y is also confused while decoding. Now this is because again the shift channel can only add zeros and doesn't add any non-zero elements. So now as a consequence of the previous proposition, if a code word is an optimal code in the p, k shift channel, then its I of x counterpart is also an optimal zero error code word in the binary shift channel. So in nutshell, we have restricted our attention to constructing optimal codes with fixed Hamming weights for the binary shift channel.
Now we consider an alternate representation for the input sequences. A binary code word x of length n in the shift channel 1, k with Hamming weight w can be uniquely represented as w tuple because it only has w non-zero elements. So basically si in the w tuple s represents the position of the ith non-zero element. The example is given in the slide. It is also trivial that if I is less than j, then si is less than sj. Shown on the first point in the slide, the new W tuple satisfies the following constraint. It also possible to do following transformation to the tuple S by making Si equal to Si minus I and obtaining a new representation which satisfies a new constraint as shown in the slide. An example for the entire process given in the slide. Also, the set of all input sequences now in the W tuple representation can be represented by a set delta W n minus W as shown in the slide. This figure now shows all possible input sequences for of length n9 and Hamming weight w. Let the binary input code word x with weight w have the alternate representation as the s tuple s. Let it produce the output z through the channel shc 1, k. The output z also has weight w and has the w tuple representation t. T satisfies the following constraints shown in the slides. This slide shows a particular example for the given settings and one particular input sequence X. We can also have a pictorial representation of the input sequences along with the output sequences as shown in the figure. So now if you consider the other input sequences as the black dots, then the possible output sequences are surrounded by dashed lines. Now we construct a zero error code for the binary shift channel with fixed timing weight W and length N. So the code words have the W tuple representation S such a way that each of the elements of S are multiples of k plus 1. So essentially now if x and y are two code words of this code with W tuples S and R, then S and R differ in at least one position by a multiple of k plus 1 where A is greater than or equal to 1. This code has zero errors because the set of possible outputs for different code words is disjoint. So as shown in the slides, the W tuples of the outputs of two different code words differ by at least one. This construction of a zero error code is better illustrated with the example as shown in the figure. So the black dots are the code words and the output sequences are surrounded by the dash line and they are clearly disjoint. We can also note that possible output sequences cover the entire output space. This property of the code is used later on for the explanation of the optimality of this code. It was shown by Shannon that zero error codes whose outputs occupy the entire output space are optimal. Using this zero error binary code constructed for the fixed weight W or the binary shift channel, we can construct codes for the complete shift channel by taking a union over W's. Now that we have the code words for the binary shift channel, the input sequences with P-ary alphabets, which have the indicator functions as these code words, are the optimal code words of the P-ary shift channel. And they are obtained by replacing every one bit of the binary code words with every element of the P-ary alphabet. Thank you.